Welcome. Thank you for joining us for today's webinar, Advanced Components to Enhance Laser System Performance, presented by Coherent and SAE Media Group. I'm Bruce Bennett, editor at SAE Media Group, and I'll be your moderator today. This webinar will last approximately 30 minutes, and there will be a question and answer period at the end of the presentation. If you have a question, you may submit it at any time during the presentation by using the Ask a Question box on your screen. Our speaker will answer as many questions as possible at the conclusion of the presentation. Those questions not addressed during the live event will be answered offline. You may also download a PDF of the presentation slides under the Event Resources tab on your screen. To view the presentation properly, please disable any pop-up blockers you may have on your browser. Now at this time, I'd like to introduce today's speaker. Dr. Timothy McComb brings more than a dozen years of laser engineering experience to Coherent. After receiving his Ph.D. at UCF, Tim worked on R&D teams at Northrop Grumman and Enlight, and later managed engineering and market applications at Andritz Powerlays and NKT Photonics. His experience in the design and applications of fiber lasers and optical fibers at the component level provides significant insight into creating high-power laser systems used globally. Now that you're familiar with our speaker's qualifications, let's begin today's presentation.
Thank you, Bruce. And good morning, good afternoon to everyone, and thanks for taking the time to listen to me talk today about advanced components to enhance laser system performance. So just a brief overview of what I'm going to talk about. I'll give you highlights about Coherent and the markets we serve. I'll talk about the laser components and manufacturing capabilities we have, touch on some applications that we do for those components, particularly in the space and defense areas. And then I'll talk about a few new products that we've recently launched to further add to our portfolio of capabilities in this area. So first, to begin, I'll give you a brief overview of Coherent. We were founded in 1966, actually in a laundry room in Palo Alto, California. The reason for being in the laundry room is that that was the only place in the house that they had available 240-volt three-phase power to power their first CO2 laser prototype, lovingly dubbed the Kludge. Since then, and since their first customer in the defense space was Boeing Labs, we've grown to a company of over 5,000 employees with 27 global locations. And our lasers are behind the technologies and technological advances that we see in life sciences, medical today, as well as a number of Nobel Prizes being attributed to research relying on our lasers. And then furthermore, we're the basis for modern semiconductor and display manufacturing as we power a lot of the manufacture of flat panel displays in the world today. We have a global service and support network to provide service to lasers basically wherever we put them in the world. So the markets we serve, here we're going to primarily talk about aerospace and defense, but we also cover the bioinstrumentation and life sciences market in things like flow cytometry, as well as lasers for a number of medical applications, including aesthetics, hair removal, and general surgical applications, as well as things like kidney stones. In the microelectronics space, we provide a wide range of laser solutions used to manufacture today's electronics, ranging from lasers used to drill and process PC boards, all the way up to lasers used to manufacture large area displays that power everybody's cell phone today. And then finally, we have a segment we call precision manufacturing, which serves a wide range of different markets, but we have a lot of focus in the automotive space, where particularly we're quite strong in the e-mobility space, providing solutions for manufacturing of batteries and powertrains for electric vehicles, as well as producing a wide range of precision laser cutting, welding, and marking machines that are used in the medical device manufacturing arena. In terms of our supply chain, I just want to take a little bit of an aside to tell you about how Coherent can really help develop and work with you as a partner, more than just being a component provider. And though I'm going to talk about components today, I want to highlight that it may be that we can also leverage in working with you some of our own experience in using our components inside of our own lasers and our own systems, And so we may be able to not only provide you with the bare components, but perhaps in prototyping or early phase, provide you with some pre-assembled subassemblies or even complete lasers or optical systems to help you move faster and focus on what you need to do and the solutions you have with your system. So with that, I'll start to kind of talk through a couple of the component capabilities we have at Coherent. I'll sort of highlight the different capabilities we have before talking about some of their applications. First of all is our specialty optics manufacturing facility, which is in Richmond, California. And there we can manufacture large format optics and mirrors and lenses over meter class in diameter. And those can be free-form optics, so really arbitrary shapes in materials like silicon carbide, beryllium, Zerodor, and basically any other typical optical material that's used in today's modern optical systems. These optics can be space qualified, as well as manufactured to be military grade and lightweight assemblies. And so not only do we manufacture the optics, but we can assemble a collection of optics into lightweight assemblies that are fully qualified to be fielded or launched into space. In terms of crystals, these are a common optical component that are used in a wide range of different kinds of systems, and we grow our own crystals in a facility in New Jersey as well as one in Germany. And there we manufacture a wide range of crystals, including nonlinear crystals used for wavelength conversion, active crystals, which are the actual gain media in lasers, electro-optic crystals, which can be used to modulate the output of lasers or be Q switches inside of laser systems, magneto-optic crystals, which are used in optical isolation and Faraday rotator devices, and then also we can process sapphire windows, which are used just to protect optical systems, but we can make those windows in very, very high volumes, thousands to tens of thousands a year, and in fact, we're one of the world's largest producer of such windows. And also we can make them to very large sizes with very high performance coatings, upwards of 8 inches in diameter with coatings that can pass things like salt spray testing. In terms of the number of crystals we grow over 25 different kinds with 4 different dopants. And in some cases, for those that need to worry about where the sourcing of the crystals come from, we can be the sole domestic option for certain categories of crystals that we manufacture. We can also take those crystals and put them into higher level subassemblies. So for instance, we can take a nonlinear crystal, mount it in an oven to control its temperature and therefore its conversion efficiency and capabilities. We can take active crystals and mount them and solder them into heat sinks, which are used to remove the heat as you pump these crystals to produce high power lasers. We take our magneto-optic crystals and assemble them into optical isolators and Faraday rotator assemblies by incorporating magnets around them. And then we can even add the electrodes to our electro-optic crystals to create electro-optic modulators that are used in Q switches and for modulating laser output power. Here you can see an example of some of the growth chambers in our facility in New Jersey, and here for scale is some of the optics manufacturing. You can see the people there to kind of give you a scale of the size of the optics we can produce. Finally, when you make all these kinds of great optics, you have to have really high performance coatings, and we have exactly that. And I believe it's up to now 4 or 5 of our facilities at Coherent have in-house coating capabilities to coat their various components. And then we have an overall group that focuses solely on improving and testing our coating capabilities and have in-house damage threshold testing as well as novel coating development capabilities. So we have a wide range of ways to assist in providing the best coatings. And we can provide coatings both like high reflective, anti-reflective, and polarization based coatings for all of our components. These coatings have been into space and they are space qualifiable, and we can make them up to meter class. As you can see off to the side here, one of our technicians standing next to our largest coating chamber that's capable of doing over meter class optics. And then finally, we can do stress analysis on these coatings, because sometimes when you make very high reflectivity coatings, the coatings can be quite thick, and they can actually deform the surface of the optic that you're putting the coating on. And so what we can do is do analysis ahead of time, pre-polish the negative of that deformation into the optic, so that when we coat it, it comes back to the desired optical form. And that's very, very important, particularly for optics that require these thick, high reflectivity coatings. Moving on to additional capabilities we have. Coherent has a full semiconductor foundry and fabrication facility based in just outside of Santa Clara, California. And in addition, we have packaging capabilities in Mainz, Germany. And in those facilities, we can grow semiconductor chips from 630 nanometers out to 2 microns wavelength. And those chips are capable of watt level to even kilowatt level power, depending on the design of the chips and the orientation of the individual emitters. We can take those wafers, dice them up into individual chips and die, and provide those to you as a customer, and then you can do your own packaging. Or we can actually put these things into diode stacks, linear arrays, individual chips on submounts, and we can then even take those and package them along with delivery fibers to produce a fiber deliverable system that can be a full light source for you. We have a wide range of standard products, but we can also customize the packages as needed to meet the needs of demanding applications or novel wavelength requirements. We also have an interesting technology called tapered amplifiers. These are semiconductor waveguides that flare from a single mode input to a broad stripe on the output, and therefore you're able to get watt level powers out of a very small chip with near diffraction limited beam quality. And this is beginning to find a lot of use cases, for instance, in the fields of quantum research, as well as in LiDAR and a number of imaging and medical applications. We also have a full in-house capability to manufacture volume Bragg gratings. These are diffractive optical devices that are used to stabilize or narrow the wavelength of the semiconductor chip. And what you do is you put the device in front of the output of the laser. The part of the laser light is reflected back into the chip, and that narrows the wavelength and selects it to a very precise place. And that means that over temperature and over power, your laser wavelength will not shift, which is very important in certain pumping applications and even just certain applications where you want the laser light to interact with certain materials at a very precise wavelength, in, for instance, materials processing applications. Furthermore, we have an entire fiber manufacturing and assembly capability based in East Granby, Connecticut. There we can manufacture active, passive, polarization maintaining fibers, dispersion managed fibers, as well as spun and microstructured fibers, and we even are now working on fibers that have radiation resistance, which is particularly of interest for fibers going into space applications where over time the radiation in space can cause degradation of performance. We have several hundred standard fiber designs that are available off the shelf and that we can ship to you today. But we also are happy to work with customers on custom designs, whether those custom designs are simple, small tweaks to existing fibers just to slightly better improve them for a specific application, all the way to a brand new fiber technology or fiber design that no one's ever tried before. We can really cover all the bases there. We can also take the fibers and put them into subassemblies. One of the things we make in quite substantial volumes are coils for fiber gyros. So these are gyroscopic navigation systems where they use an optical fiber to do inertial navigation. But we can also build the fibers into fiber-coupled components using some of the other components I've already mentioned, for instance, optical isolators or some of the coded ASE filters. We can fiber-couple those devices, put end caps on them so they don't damage at high output powers, and then build them into the key components for high-power laser systems. We can also manufacture fused fiber combiners in certain cases. And then finally, while we've mostly talked about true components that you would build up to put into a laser, we can also consider laser subsystems as components to even larger systems. For instance, our kilowatt fiber amplifier modules are used quite substantially in the directed energy space, and you can take multiple modules, combine them spectrally or coherently to achieve tens of kilowatts or more of output power. We also make a wide range of sensors and photodiodes that can be used to monitor all of these laser systems that you're developing. We make structured light and machine vision type illumination lasers that can be used in laser tools to help guide the final laser beam or to help machine vision recognize certain components. And then we make a wide range of other standard visible UV laser systems as well as IR laser systems based on CO2 and ultrafast lasers both based on titanium sapphire and ytterbium-based gain media. So we really cover a wide range of laser capabilities, and so these can all be subsystems that could be designed into a larger photonic product. So moving on to some applications, one I always like to start with is talking about the lasers and optics we've put into space or have getting ready for space missions. And the biggest one there is from our group in Richmond, who have been making space-based large format optics since the 1960s. They've flown over 100 successful optical missions, both being put into Earth orbit for observation missions, but even being put to other planets and even outside of the solar system. We have optics on the Voyager spacecraft. We have optics on the New Horizons spacecraft, which are also some of the fastest moving optics ever, since that spacecraft is moving at something like 35,000 kilometers an hour, something of that nature. We also can provide those optics not only as individual optics or just coded mirrors, but we can build them into subsystems, as you can see here, the example of the New Horizons telescope subsystem. In terms of coatings, as we've already talked about, we have flight qualified both metal and dielectric-based coatings to make these mirrors have the appropriate reflectivity. We've done coatings on optics, for instance, for the James Webb Space Telescope that's soon to be launched. In terms of crystals, we've put a full array of laser crystals and into space on the NASA ISAT-2 mission. This was a green neodymium vanadate-based laser, so we made the active crystals. The laser was then frequency doubled with our LBO, and we also used RTP and modulators used to Q-switch the laser. So overall, this was a mission used to measure the thickness of ice on the poles. We've also put a number of Faraday rotators and isolators into orbit on a number of other space missions. On the laser front, we have 976 nanometer fiber coupled pumps you can see down here being qualified to be used as pump lasers on a number of different NASA missions. In addition, the JPL Lunar Illuminator is getting ready for launch, and there we have a stack of multiple different wavelength diode bars that are going to be used in that system. And we even put a CO2 laser, a carbon dioxide laser, into space, which was used to pump a terahertz gas laser on the NASA Aura satellite, which was launched back in the early 2000s. From the fibers perspective, we've put fibers in spectrometers to deliver light from the collecting optics down to the spectrometer on the Curiosity rover, and have a number of qualification efforts ongoing for some fiber designs that are radiation resistant for other space applications, particularly in optical communications in space, laser communications. And then some of our fiber gyro coils have also flown on commercial spacecraft. Moving on to applications in defense. This is one of the places where we see quite a strong capability for a lot of our laser systems, and one of the most common places you'll see lasers in the defense space are in laser rangefinders and laser target designators. And there, the types of things we manufacture for this space include semiconductor lasers used to pump these systems, as well as optics used in the beam delivery chains of these systems. You can see an example here of an all-aluminum mirror, which has an aluminum polished surface for thermal management and light weighting of some of these devices, particularly in handheld devices. And then we also manufacture the crystals, the laser crystals and the nonlinear crystals that are often used to shift these devices from 1 micron to eye-safer wavelengths, for instance, in 1.5 microns. LiDAR is quite a hot topic today, both in the commercial and the defense space. You're seeing a lot of it, of course, in autonomous vehicles for automotive, but of course there's also autonomous defense vehicles, as well as the desire to do terrain mapping and other types of 3D LiDAR applications. And there, we of course serve that with, again, laser diodes for pumping, all of the optics used in telescopes and beam delivery, as well as the crystals. Oftentimes these LiDAR systems are quite high repetition rate, tens to hundreds of kilohertz, tens of watts of average power, and nanosecond class pulses. And to do that, usually you'll use something like a neodymium vanadate crystal, or perhaps a fiber amplifier to achieve those high energies and high average powers that are needed for LiDAR systems. Infrared countermeasures has been around for a long time as well as a laser application. This is used to generate infrared light in the 2 to 5 micron range, which is a range that is used by seekers on various missiles. And so you can generate light with these lasers to help confuse those sensors and to protect aircraft. There, you're again manufacturing usually a 1 micron laser pump source that then is converted via various crystals that we can also manufacture that shift the wavelength out from 3 to 5 microns. The other way to make IRCM systems often is to manufacture a thulium fiber laser at 2 microns, and there we manufacture both the thulium fibers and the pump diodes that can be used in such systems. And then again, you can convert those directly to the IR from 2 micron with nonlinear crystals. Laser dazzlers are also becoming quite common. These are both dazzlers used to distract personnel, but also can be used to distract or otherwise blind sensors in for instance, unmanned aerial vehicles that are doing, for instance, surveillance that you don't want to have happening. And there, it's often a green laser, but it could also be, particularly in the case of sensors, it could be an infrared laser that's used to temporarily disable those kinds of sensors. One of the largest and soon to be really dramatically growing spaces in defense is the use of directed energy for applications, particularly to shoot down, for instance, things like mortars and missiles and unmanned aerial vehicles. And there, Coherent is very, very active in this space. We manufacture kilowatt-class laser modules that can be combined into higher powers. We're one of the largest provider of those modules in many cases. But we also manufacture the pump lasers and the fibers that go into them. And so if you want to build your own as opposed to using one of our modules, we can help you with the subcomponents, optical isolators and fibers that go into those systems. And then finally, we manufacture the actual delivery optics in these systems, because here you're talking about hundreds of tens to 100 kilowatt class average powers. And so you need relatively large optics with very, very high reflectivity coatings. And this gets back to where I was talking about earlier about making sure your coatings aren't stressing your optics and deforming them. You can see here an example of an analysis on a thick coated optic, where because of the light weighting that happened on the backside of it, when you put this coating on it, it deforms the optic, and therefore you need to pre-compensate that when you polish your mirror before coating. A space that's also gaining more and more popularity, particularly commercially, as you see lots of spaceborne internet, is laser communications. And there's an actual NASA mission that we've participated in where we built a primary mirror to send light out, to show feasibility of sending light out towards spacecraft to communicate them with much higher communication rates. And we used one of our kilowatt class modules originally designed for directed energy, but also useful in these laser comm applications. And this supports a NASA mission that's ultimately going to try to put a spacecraft out in the asteroid belt and do direct laser communications to that craft. And then finally, a couple of categories: sensing and imaging. This is your typical satellites looking down on the Earth, using imaging systems with cameras, and there, of course, our optics group in Richmond manufactures a wide range of different assemblies and arrangements for those kinds of systems. And then navigation, you see a lot of lasers being used, particularly to drive the light sources in the gyro coils that we manufacture as well. So moving on to some of the specific new products and capabilities that we've added over the last few months. The first is a full company that Coherent recently joined the Coherent family, and that was a company formerly known as EOT. And they manufactured Faraday rotators and optical isolators, which are key components in almost every laser system you can imagine, from UV all the way out to 10 micron CO2 wavelengths. They have components that can actually handle up to 2 kilowatts of average power, which is, again, critical for some of these high-power directed energy applications. And also can take some of these components and fiber couple them and fiberize them with built-in fiber terminations to manufacture compact high-power isolators that are key in directed energy amplifier systems. We can also manufacture at this site photo detectors that can be fiber coupled and pure terminations that are used for the output of a variety of different laser systems. Just to give you an idea of the breadth of capability, here's the overall optical isolator capability we have at this site. So as you can see, it covers anywhere from visible light down in the green range all the way out to 10 microns at powers well over 400 watts. Another product line that we recently launched is our Factor line of fiber-coupled single emitters. So what this is an array of different single emitter diodes, all combined via optics to produce a single output with up to 22 individual emitters and 400 watts or more from a single package. And these are commonly used to pump very high-power fiber lasers, but the 800 nanometer versions can also be used to pump neodymium vanadate crystals, for instance. Our kilowatt-class optimized fibers were developed for industrial laser applications where materials processing with multiple kilowatts is needed. In this case, we can do single-mode beam quality with up to 3 kilowatts, designed for both pumping at 915 or 976 nanometers. But these can also be used in amplifier configurations, not just the oscillators that are more typically used in industrial. and that's where they can be used to potentially support certain high power applications such as directed energy. Another area growing in interest and where we've started to support is thulium fiber lasers. These are 2 micron wavelength lasers, which is in an eye safer regime compared to 1 microns. You're starting to see a lot of interest, and therefore we've got fibers that are doped with thulium to produce this wavelength, and we also manufacture pump lasers up to 100 watts at 793 nanometers, which is a very common pump wavelength, to take advantage of the high efficiency cross relaxation 2-for-1 pumping of thulium fibers. And then finally, we have fibers that are optimized for ultrafast laser amplification. But when we say ultrafast, really it's just for any sort of high peak power pulsed lasers, anywhere where you want really low nonlinearity in your amplifiers. We've got a number of different fibers that have been designed to minimize the length of the fiber while not sacrificing photodarkening and lifetime properties of the fiber, and still maintaining high beam quality in terms of output performance. And so these fibers, we looked at all the way back from the composition, the fundamental composition of the fiber, to really optimize that from square one to make sure we dramatically enhance the emission and absorption cross sections, and therefore didn't need to dope as highly and thus achieve better photodarkening performance from the fibers overall. Again, we've talked about most of these fibers already. I'll highlight that the erbium and terbium fibers are designed for both radiation resistance for optical communications in space, as well as automotive LiDAR, and that's a new fiber that we've recently put out on the market. And so with that, I'll wrap up and take any questions you might have, and thank you again for your attention.
Thank you, Dr. McComb, for such an informative presentation. We'll take a few questions now, and before we start, let me remind our audience that if you have a question, you may submit it simply by using the Ask a Question box on your screen. Okay, first question. Do you make any sweeping lasers? If so, what is the line width?
That's a good question. So today we don't manufacture any sweeping lasers directly, but we do make, when I refer to the tapered amplifiers that we talked about, those are amplifier devices. And so you can build a system around those tapered amplifiers, for instance, with an external grating that can then be mechanically moved. Or, for instance, you could use a micro-optic device or a MEMS device to do that same sort of thing. And often you see that used to then sweep the wavelength over a pretty wide range. And in that case, they can achieve quite narrow line widths, but it's all down to the design of your own laser cavity. And I think you can get down to tens of kilohertz, if I remember correctly, that some of our customers have used these amplifiers to achieve.
Thank you, Doctor. Next question. Can you write Bragg gratings onto polarization maintaining fiber? If so, what is the cost per meter?
So that's a good question. So I don't have the specific cost per meter with fiber gratings written into it, for instance. Certainly gratings can be written into polarization maintaining fiber. It's not currently a capability we have in-house, but we do know, basically we have partners who can write such gratings. And so if you're interested, definitely reach out to us. We can work with you on picking the right fiber and then pointing you to the right people who can manufacture the actual gratings. In terms of the cost per meter just for the fiber, it's usually a few tens of dollars per meter, but it really dramatically depends on the how much fiber you're buying and also the specific properties of the fiber.
Thank you, Doctor. One of our attendees would like to know, do you only do the lasers or also the housings and mountings?
So in terms of the housings and mountings, I guess it depends on the context. So for a lot of defense applications, usually our customers tend to take our laser systems and build them into a much larger assembly. But we could, for instance, take the lasers and build them onto a plate along with other components. So in certain industries, for instance, in the flow cytometry industry, we often take multiple different color lasers combine them into a single box, and then put them into a fiber so you have all the colors coming out of a single fiber. So we can do certain kinds of subsystems. It really depends. We also manufacture laser tools where we'll take some of our lasers and build them into big cabinets that are used to do materials processing. So really it's a pretty wide range of capabilities, but if there's a specific kind of housing and kind of packaging you're interested in, definitely reach out to us offline and we'd love to chat about it.
Thank you. Next question. What is the highest power your isolators can handle?
The highest power our isolators can handle are on the order of 2 kilowatts of average power at 1 micron. That's sort of our hero results at the moment. The standard products are usually rated for just under 500 watts of output at that 1 micron regime. But we're constantly pushing the boundaries, so we'd love to hear if you have new challenges.
Thank you. Are your ultrafast lasers optimized PM fibers useful for applications besides UF lasers?
Yeah, actually, as I sort of alluded to, when really the fibers are about, we call them ultrafast optimized fibers, but really they're optimized for low nonlinearity. Ultrafast lasers tend to care the most about these kinds of nonlinearities, but when you're looking at systems like LiDAR, where it's high peak power pulses in the nanosecond regime, the fibers can again help to remove those nonlinearities and allow you to get higher power than you otherwise would from a fiber, while still maintaining the benefits of a fiber and not having to go to a solid state laser, which can often require a lot more mechanical interfaces. So indeed, they do extend quite a bit beyond the regime of ultrafast lasers.
Thank you. I'm afraid that's all the time we have today. I'd like to thank Dr. McComb for giving us such an enlightening presentation, and I'd like to thank today's attendees for participating. That concludes today's webinar, sponsored by Coherent and SAE Media Group.